So in this video, I just want to talk a little bit more about exponential modeling. So we'll use a mouse population. So you can see the mouse population triples every month. That's a little frightening. If it started with 50 mice, then I got several things you need to do here. So first, part A says write a function to model the mouse population based on time. So as you saw in the first introductory video, there's really two basic exponential models. We have y equals a times b to the t, or y equals a times e to the kt. And we could really use either one of those models here. If we're using the first model, we'd have to find out what b is, because we've been given a, right, the initial population. And if we're using the second one, we'd have to figure out what k is. So let's do the first one first. So we know that it would be y equals a, well, a would be 50 because that's the initial value. A would be 50 times something to the t. And what do we know? Well, we know that it triples every month. So after 1 month, it's going to be 3 times as big. Okay? So that means I could rewrite this as 150 would be what happens when you triple 50. I would just put a 1 up here. So what does that mean? That means that we need a 3 in there. Okay? Well, if you don't see that, then we could just put a b there and divide by 50, and we get 3 is equal to b. So that means the function model would be y equals 50 times 3 to the t. So this is a model that I could plug in the number of months, and it would tell you how many mice are in this, wherever this is. Okay. Now the other option would be to use this second model. And remember, in the initial video, I make it clear that b is equal to e to the k. So since we already know what b is, we know that b is 3. We could write a little formula over here that says 3 is equal to e to the k, and then I could solve for k. And you guys all know how to solve for k now, right? Because you got to remember, e is just a number. So I'm going to take the natural log of both sides. So we got natural log of 3 is equal to, and the natural log of e to the k would just be k. So we come up with k is natural log of 3. And if I grab my calculator, let's see, natural log of 3 is approximately 1.098612. So then another way to write this model would be to say, let's let y equal 50, because it's the same initial population, times e to the 1.098612t. So either one of these would work. And notice if you put a 1 in there, you will get 150. And if you put a 1 in there, you'll get close to 150. Probably won't be exact on because we had to round off there. But let's try that. E to the 1.098612. You get 2.999999 times 50. And sure enough, we get 149.999, which would be 150. Okay. So there's your two models. Either one of those would work. This one seems to make the most sense to do on this one because we already know there's tripling, so it's pretty easy to see that we just put a 3 in there and then put months up there. Now, the second one says, how long will it take to double? So knowing that it triples every month, how long will it take to double? Well, we already have a formula. Now we could use this one or that one. And so what we're going to do down here is say, let's let y equal 50 times 3 to the I don't know. And if we want it to double, what we're going to do is put just 100 over here, because that's what 50 doubled would be. So then by doing this, we could figure out what the t is. So of course we divide everything by 50, that'd be 2 equals 3 to the t. Take the natural log of both sides, so that'd be natural log of 2 is equal to t times the natural log of 3. So that means that t is going to be equal to natural log of 2 divided by the natural log of 3. And if we throw that into our calculator, we get natural log of 2 divided by natural log of 3. And we get t is approximately equal to 0.6309. And we probably don't need to go way on that because we're trying to figure out how many months it takes to double. Well, this says 0.63 months, so that'd be less than a month, which is not surprising because we already saw that up there. It takes 1 month to triple, so obviously it's going to take less than a month to double. Now let's just to play around a little bit. What if this, instead of saying the mouse population triples every month, let's say the mouse population triples every 2 months. How does that change anything? Well, that means down here that this would be a 2, but everything else is going to be the same, right? Because I'm still tripling, right? So I'm going from 50 to 150, that's a tripling. And this, but it's b to the second power now because it takes 2 months for it to triple. So then I would divide this by 50 and I get 3 is equal to b squared, which means the square root of 3 is equal to b. So then I'd go back up here, and in place of 3, I'd have the square root of 3. And of course I could turn that into decimal. And then the same thing happens over here. We know that this is equal to the square root of 3 now, right? So that means this would be a natural log of the square root of 3. And if we do that, that would be clear. Natural log of the square root of 3. So we get approximately 0.549306. So that would change this to 0.54. Oh, wait a minute. Did I do that right? Let me try that again. Natural log of parentheses, no. The square root of 3, close parentheses. No, 0.54. Okay. 0.549306t. So this would be the model if it triples every 2 months. So basically we're taking the amount of time it takes to do whatever it's going to do and put it in for time, and then we're looking at what this says to figure out what to do with that side. Okay? Okay. Now, part C, how many mice will there be after 1 year? So depending on if we're going off of this one up here now, we would just take this one of these equations and come it down here, and we'd say y equals 50 times e to the 0.549306t. And it says how many mice will there be after 1 year? Well, now be careful here. It's tempting to just put a 1 in there, but remember up here, this whole the modeling was based on y as number of mice and t is number of years. And sometimes it's helpful to write that. Equals number of months. See, I already didn't write it down, so I almost forgot. Because remember, we measured it in months, right? So when I get down here, I can't plug in a 1 here. I have to plug in 12 here because there's 12 months in a year. So then I would throw that in my calculator. So I would get, let's see, e to the parenthesis 0.549306 times 12. And then multiply that. Whoops, I did that wrong. Sorry. Be careful where you put your 12. Okay, this should have been e to that. Put a parenthesis in there. 12 times 0.549306 close parenthesis equals times 50. And so in 1 year, and this is going to be frightening, so brace yourself, 36,449.9 mice, so we probably round it up to 50. So 36,450 mice after 1 year if they keep growing like that. Okay, so now let's say that the mice are overrunning our place, so we get a couple of cats, and now the mouse population is decreasing by 10% every month. So put a little d down here, mouse population declining by 10% each month. Okay? So basically we're going to start with a new one. We got y equals 36,450. We can kind of ignore that old formula because now it's something that's different is happening. So we got 10, and it's decreasing 10%. Now remember, I told you that b is equal to e to the k, but I also told you that b is equal to 1 plus the growth rate, or decay rate. So in this case, we have a decay rate of 10%. So that means my b, because I'm going to use the y equals a times b to the t here, my b is going to be 1 minus 10%, or 1 minus 0.1, so this would be 0.9 to the t. So that means, another way to think of this is, if it's declining 10%, I would multiply by 90% to find out what's left, right? If I'm losing 10%, that means I'm going to have 90% of what I had. So that's the formula for the mouse population declining. And let's say that we wanted to A, B, C, D, E. Whoops. We wanted to know, okay, now how many mice after 6 months. Okay. So once again, this is still measured in months because they said each month, right? So then we get y equals 36,450 times 0.9 to the 6th power. Okay, so we grab a calculator and we go, let's see, that would be times parenthesis 0.9 close parenthesis to the power of 6. And we go after 6 months, the population would be down to 19,370. No, 0.99, so we'll round up to 371. Okay? Now let's say a horrible rat disease came in, ABCEF, and now they're dying off at declining at 3% a day. So we're going to take our most recent population, the 19,371, because that's what we know now. And since I'm declining 3%, that would be 0.97, because it's 3% less than 100%. And we would put a t up there. That would be the model. And let's say we want to know what happens after, say, 2 months. What's the population going to be after 2 months? So, but now notice we're doing it per day, because our decay rate is based on a daily decrease. So if I'm trying to find out how many So how many mice after 2 months? Well, I'm going to have to put in y equals 19,371.97. But instead of putting 2 in there, I remembered that this is based on days because this is it's losing 3% a day. So this should be counting days up here. So I'd have to put 60 days in there. And so then I get, whoops, clear 19,000 times parenthesis 0.97 close parenthesis to the power of 60 equals. And now after 2 months, the population is down to 3,114. 0.98, so I rounded up to 115. Okay. So hopefully there's a bunch of examples of how to handle the oh, actually, one more example. Let's figure out what the half-life of the mouse population is. Since it's declining, we could talk about half-life. So remember, to figure out half-life, what I'm going to do is I'm going to take half of 19. So I would do clear 19,371 divided by 2. So I want to know, when does it get to 9,685.5? Which of course you can't get 0.5 mice, but we're just doing this to figure out what the half-life is. So then we're going to leave a t up there, because when we're asking what is a half-life, we're trying to figure out how many years does it take for something to lose half its stuff. Now usually we don't talk about half-life in a mouse population, but I just kind of wanted to throw this math in here while you're at it, because this is something else you need to be able to do. So what is the half-life is what we're asking right now. What is half-life? So see, what we've done is we've taken the initial value, divided it by 2, and put it over here, because we want to know how long it'll take for this to be reduced to half of what it was. Okay, so now if you divide this into that, you get 0.5. So really what we're trying to figure out is, when is 0.97 to the t equal to 0.5? Okay, and so once again, this is an exponential equation, so I can solve by taking the log of both sides. So I get the natural log of 0.5 is equal to t times the natural log of 0.97. Divide by that, and I get the natural log of 0.5 over the natural log of 0.97 is equal to t. So then I throw that in my calculator. Clear. Natural log of 5 divided by natural log of 0.97 equals, and I get it would be 52.8. It's 3% a day, yeah. So it's going to take 52.8 days for the population to be cut in half. You know what? I did that wrong. Let me run that again. Natural log of, I think I did it 5 instead of 0.5. Natural log of, there we go. I didn't think that's all right. Yeah, okay, I got 22.75. That sounds better. 22.7-ish. So the half-life of this population would be about 23 days. It's going to take about 23 days for the mouse population to be cut in half. Okay, so there's a bunch of examples of just kind of doing the different type of things that you need to be able to do with exponentials. So hopefully this helps to clear some things up.